you for joining us for our latest webinar with TRUMPF. I'm Nick Holtz, editor of AMS. This webinar is focusing on the growing momentum behind the use of laser welding of powertrain components. Over the next half an hour, we'll be joined by Oliver Mullisham and Hakan Kenderci, who have responsibility for TRUMPF powertrain applications worldwide. Together, they bring a wealth of experience of laser technology with powertrain applications, and they'll be giving us an overview of a number of processes and production solutions to manufacturing challenges that they've encountered. Now, before we start, I'd like to remind all of you in attendance to draft up some questions which Oliver and Hakan will be pleased to answer in the Q&A session following their presentation. Please ask these questions by typing them into the box in the lower right-hand side of your screen. They will also be asking you to participate in an online poll, so please do look out for that at the end of the presentation. Now, if you should happen to experience any technical issues during this session, please also type these into the Q&A box, and our team here will do their best to sort these out for you. We hope you'll find this webinar stimulating and informative, and I'll now hand over to Oliver to begin his presentation.
Okay, thank you, Nick. Ladies and gentlemen out there all over the world, it's a pleasure for us to tell you about our latest innovative laser applications and production solutions for powertrain components. On the first slide, it's our agenda. We want to provide you some information, some short information about the company TRUMPF, what we are doing. The next one is typical laser applications in powertrain, and of course some trends in powertrain. Followed by more detailed information about laser welding solutions for differential gears, for drive shafts, drive flanges, and for the dual clutch systems. After this part, we will switch on to TRUMPF machine solutions, integrator solutions, and marking processes. And in the same way, we can use these laser systems or this technology to clean parts prior to the laser welding process. Structuring of tribological surfaces will follow, and of course at the end we will give you some ideas, some research topics. One of this is going to be online thermography, and the last one is going to be laser welding below atmospheric conditions. The end, the conclusion. So let's start now. Some information about TRUMPF, some typical laser applications in powertrain, and of course some trends in this field. First of all, TRUMPF, we are a high-tech company for laser and machine tools, and we have approximately 10,000 employees worldwide, and we are represented in all world markets, close to our customers with about 58 subsidiaries. TRUMPF is divided into three parts. The biggest one, this is our machine tools, where we are producing flat-bed cutting machines, bending machines, punching machines, all for the sheet metal process. The second biggest part, this is where we are from. This is the laser technology of TRUMPF and the electronics field. We are producing solid-state lasers, we are producing CO2 lasers, and of course 3D machines, for example, underneath that part for cutting and welding process, what we're going to show you later in more details. The electronical field of TRUMPF is we can supply, even in the powertrain field, machines with induction preheating system, for example. And the third and the youngest part here on the right side, this is the medical technology of TRUMPF. We are producing equipment for operating rooms and intensive care units. Let's switch now to the laser technology of TRUMPF. Here on the left upper side, you can see we are producing CO2 lasers from 700 up to 20 kilowatt output power, and solid-state lasers in different kind of areas. We can use these solid-state lasers. This is what I'm going to show you later in my presentation. Of course, marking systems, what we are producing at TRUMPF in Switzerland, are used even for the powertrain business for marking parts, to mark a DMC code, for example, for the traceability. Even this one will show later in the next slides. The 3D machines, what you can see on the right upper side, this is an example. Our TruLaser Cell 7040 is mainly used for cutting processes, for example, for hot formed parts which are not, or we cannot punch these materials anymore. They're really hard, so we can use these machines to cut, for example, a B-pillar of a car made of these hot form parts. Let's come now to the field of powertrain. Some typical application, it's divided within TRUMPF into two groups. On the upper side you can see some examples of gearbox components. You can see a conventional gear part like this one or a differential gears. What I'm going to tell you, or more detailed in the next slides, of course the technology of double clutches, what you can see with this picture, is a very famous application worldwide. Even the automatic transmission, like 8 or 9-speed automatic transmission, nowadays up to 10 gears, is the laser is used for such typical application in the field of welding of powertrain components. On the lower side you can see some examples of engine components. Here are some parts of cams, for example. A very important thing in the next few years, our upcoming technology is to use steel pistons instead of aluminum parts, and of course the turbochargers. This is a very common technology to reduce the consumption of a car in the next future. Some trends about combustion engine, you can see here some examples again. Of course the turbochargers is going to be a really important thing, and the downsizing of engines, this is really important. You can see some examples here, even the steel pistons again, the same on the side of the transmissions. I already mentioned the technology of the double clutch or triple clutches, what we're going to have in the market, and of course 8 to 10 speed automatic transmissions where we are welding with our lasers and systems a lot of different parts, what I'm going to show you later. So let's come now more detail to these applications. I want to start with a very interesting thing. This is laser welding of differential gears with and without filler wire. So both applications are in mass production. Next slides you're going to see more details about this. Laser welding and with an induction preheating system is sometimes necessary when we have parts or two partners, material partners with a high carbon equivalent. Then we can use also our equipment for preheating prior to the welding process. Last one here in this part, it's going to be laser welding of double clutches, where we can show you a cross-section of such a double clutch where you can see a lot of different laser weldings made with our systems. Let's start now with the area of the differential gears with, and this is the reason for the blue colored with additional material, because some slides later I'm going to show you the same combination of cast material for the housings and case hardened steel for the ring gears, for example, joined with a laser without any filler wire. But let's start with the conventional one. Here you can see a typical cross section on the right side. This welding is made with a solid state laser with a filler wire system, wire feeder system. Typical materials, you can see it here on the left side. Also an example for wire material. Typical laser power for this application is about 4 to 5 kilowatt. And here in this example, I can show you a short movie. You can see our welding head, which is equipped with a wire feeding system and a sensorical system to find the right position. Then we can start directly here with the wire. Typical laser welding speed is about 1.5 to 1.7 meters per minute. And you can see a typical cycle time, this is a very short one, is about 30 seconds. The welding time itself, it's about 50 to 20 seconds. This depends on the diameters of the parts. What was the idea to weld these parts? You can see here on the right upper side the old bolted version. You can see these bolts here. As I think it's quite easy to understand, this is a very expensive application. So in 2004 we started to develop with some partners and companies like BMW, for example, to weld these parts instead of using bolts for the joining of these two parts, the housing and the ring gear itself. What was the idea? Of course, to reduce the costs. On the same side, it was very important to save material in the same way to reduce the weight of these parts. And to make it possible, I think it's quite easy to understand if you see these dimensions now. With the bolted version, we have a big flange here, a big D diameter, and the thickness was necessary to join these parts. With the laser welded version, it's quite easy to see the thickness is much it's thinner, and even the diameter of these housings could be reduced, so it was possible to reduce the weight here. Nowadays, this is mass production, and we have a 360 degrees laser welding to join the ring gear to the housing itself. In the same way, it was also possible to transmit larger torques and to reduce or to change the noise emission while using the car. This was also very important for our customers when we developed this application. Just an example here of installation in the US, where we are producing a lot of these parts for a big car maker in the United States. The first step is always to clean the parts. That means with the first station, this is just an example, nowadays it's much smaller with the latest technology, we can clean the ring gear, for example. That means the surface where we have to join the partners, and the housing, which is made of cast material, with the laser technology instead of a washing machine. That means, this is going to be shown later in the next few slides, the washing result is a very stable one, and this can be positioned prior to the welding process. This is the machine, what you can see here in the left back side here. This is a laser welding machine made by TRUMPF with 2 rotary tables here. So we have to place with the robots the washed or the clean parts, and then we will join it, we will press the parts, and we weld it in the same rotary table. Just to give you an idea about this, there's another small movie, a short movie. The robot will pick up the raw parts here, the housing and the ring gear, will place it to the laser cleaning station. After the cleaning process, it will be placed to one station or the second station of the laser welding machine and the back here. So internally, we have the press step and the welding step. After this operation, we have to bring back the welded part to the same workpiece holder, because the bevel gear is already joined to the differential gear. Several years ago, there was an idea to weld these 2 partners, and the same partners again, the housing here, cast material, and you can see the material with the GJS here 600, and the ring gear, mainly a case-hardened steel is used, and there was the idea to weld it without any filler wire. But the problem is, it's a kind of hardening process, because the carbon content, especially of the housing, is very high, and there's a risk if we go higher than the 400 HV with the hardness of the material, there's still a risk for cracks. This was the reason why mainly all the applications worldwide, they're using the filler wire to join these 2 partners. But anyhow, there was the idea, what happens if we mix the materials here, material 1, for example, the cast material on the right side and the case hardened steel here on the left side. If we are able to mix it in the right way, there's a special thing with the hardness. If it's done in the right way, there is one position or one mixture, carbon mixture here, which allows to weld the parts without any wire and to reduce or to get a lower hardness. But the challenge is we need a very precise positioning of the laser beam, and it's still a small process window. Therefore, we developed a special sensorical system. It's called TRUMPF Seamline Pro, together with a car maker. This sensorical system is able to detect 3 different steps with one camera. The first one is the pre-sensor, so we can measure the joint. We can see where is the joint we have to weld or to position the laser beam. In the same way, we can measure or get some information with our in-sensor. With this sensor, we can have a look directly onto the keyhole, the process itself. We can see absolutely the center of the focused beam and the welding process. With this sensor, it's also possible, if the part is designed in the right way, to get information if we have full penetration reached or not. And in the third way, we also can have information about the quality of the surface of the welding with our post sensor. That means we can get information about if there's an overfill or a groove or an undercut, for example. So we can provide some information about the quality of this process. With this system, we can document a lot of data for the traceability, because we will store many pictures made with our camera system. You can see here this is a welding head made of TRUMPF, and this is a special camera system. So it's also possible to send a lot of information for the quality process for our customers. Just to show you what happens here, when we use this system, you can see in the green field here, this is the preparation of the parts, the gap pressure preparation, or the chamfers, what you can see here. In the red part, you can see absolutely the center of the welding process, and on the left side here in the blue part, we can have information about the surface of the welding itself. In the same way, as I already mentioned, we can have a full penetration detection. If we have this in sensor, I'd like to bring it a little bit forward. You can see now this little cross, this black cross. This gives us information about full penetration, because this is the end. We have a complete look through the keyhole. If we see this, if we detect this, we can provide information that we have full penetration. This is an example of Daimler in that slide here. On that slide, you can see it's in mass production, welding without filler wire of these two joining partners. You can see the part itself here, and a very thin and narrow welding seam here on the right side, made without filler wire. The speed, the welding speed itself, it's 3 times higher, or up to 3 times higher, compared with the conventional laser welding process with wire. In the same way, of course, you can save a lot of costs, because we don't need wire. But if you like to start such an application, we need to develop it together with you, because we need a special preparation of the part itself. So let's switch now to another application. If we have also a lot of carbon equivalent with the two joining partners, very often we are able, or we have to use induction preheating system within TRUMPF. We are also able to provide such an inductive generator, HF generator, for a preheating process. I will show you here some details about such a typical application with this example of laser welding of dry flanges, or flange tulips. And I just want to start this movie here. So at the very beginning, we will receive already pressed part with this conveyor system. A robot system will pick up the part and will place it to the rotary table, where we join and clamp the parts. Then we will dial the table to the next station. The second one is the preheating station. Now you can see the inductor here, and we will heat up the part, and in the parallel way on the third station we can weld the part. So we can do it in the same time. You can see now the part here a little bit gluing. And the third step, as already mentioned, is the laser welding process, a deep welding process. Here in this example, it's about 5 to 6 millimeter deep penetration here. Temperature with this induction preheating system before we start to weld is about 450 to 500 degrees centigrade. With this process, we are able to reduce the hardness, that there's no or just a little bit of mud inside structure of the material. After the welding process, we will bring it back to the next exit conveyor. Third application here is a very common one worldwide. This is laser welding of dual clutches or double clutches. Especially Volkswagen started with this application some years ago, together with the company BorgWarner, where we developed this process. You can see here some references. I think all of you know about this technology. It's a very fast gear changing. There's no interruption of traction. It's a very good feeling to use such a technology in a car. It feels like a race car. It's funny to use it. Here's such an application what we started with in 2004, 2005. This is one of the first double clutches produced in mass production. This is the DQ250. You can see a cross-section of this part, and a lot of these laser weldings here. You can see these little pictures around. These are all laser weldings made with our systems to join the hub and the inner parts and the outer parts here, as you can see on this example. Here you can see the complete gearbox. The double clutch itself is here, this black round thing what you can see here. Behind this double clutch there's a gearbox, which you can see. Even here we have a lot of laser applications. Here's some references, some ideas. So since that time we started a lot of productions worldwide to produce different kind of double clutches. What you can see here is just some examples and references where we are producing with our lasers and machine systems these parts. Let's switch now to I want to give you some ideas about machine solutions made by TRUMPF. And at the same time, if we need a fully automated production line, we have a lot of partners worldwide, and even here I want to give you some examples for a mass production system. Let's start with this machine. This is a new development within TRUMPF. This is our TruLaser Cell 3000 series. It can be equipped with a rotary or a dial table and a C-press, which you can see here, to join the parts, to press the parts, to hold them down while we are welding these parts. It's a very compact system, what we're going to see now in the next movie here. You can see this is equipped with a dial table. This is just an example, this part what we see now. As you can see, it's a very compact footprint. All the safety enclosures are already around, and it's quite easy to change from a cutting process to a welding process just by changing parts of the optic. So while we are welding inside later, you're going to see it in the movie, we can load and unload outside in a manual way, or can do it with a robot, it doesn't matter. You can see outside we can load unload while we are welding inside. This machine can be also used for a 3D cutting or welding process, what you can see here in this example. If we bring out the part, it can be transported to a conveyor system, and as I already mentioned, we can load and unload again with the robot outside. What we need, of course, is the laser source, the solid-state laser. In a few seconds you're going to see it. Here it's a true disc laser, for example, and a chiller device, and the extraction system is needed for the welding fumes coming up from the process. But as you can see, it's a very compact principle and very nice and small machine. Very often, of course, we have to quote a big machine system together with our partners. Here's just one example of company EMAG, for example. They are integrating our TruMark lasers for example, for a marking process or cleaning process, and of course the TruDisc lasers series of TRUMPF for the welding process itself. Here in this example you can see another welding process for differential gears. Second partner, just as an example, is company Felsomat. With this company we launched 1 year ago the first production lines for the 8- and 9-speed automatic transmission of ZF, which you can see here on the pictures in the United States. Here on the back side of the machine you can see the TRUMPF solid-state laser, and we can bring the laser via this flexible fiber cable to the welding cell inside of this machine system. Here I'm going to show you some advantages of the laser welding process. I think it's well known already. Of course, we can weld with a very high speed. We have a really low heat input and a low distortion with this welding process. We have a high welding seam quality, of course. We can join different materials, what I showed you in the last few slides. We have a high process and geometrical flexibility with this technology. It can be easy and highly automated. And I think this is also interesting for you. We can weld under atmospheric and below atmospheric condition, what my colleague Mr. Hagen Kendici will show you later at the end of the presentation. At the end, of course, for our customers, it's very important to save costs and to have a really flexible system for their welding process. Let's switch now to laser marking. I think this is a well-known application. You can see a typical example of a DMC, what you can see here on a ring gear, on a bevel gear here, for example, or on a conrod, what you can see here. We can use a comparable technology also for a cleaning process. Prior to a welding process, we can use it instead of a washing machine. Just want to give you the idea. Here you can see a ring gear. This is the surface after the cleaning process. It's very clean, and we are also able to remove a complete layer of the surface of the material, but of course also we can remove oil, grease, and so on. This improves the welding result itself, so that means we have less spatters, we have a complete cleaner process. Just to give you an idea, this movie is made in our lab here. It's the ring gear. You can see this black colored surface here, or layer. This is phosphatium layer in this example. And as you can see, within a few seconds we can remove it completely from the surface. So we have the blank material on the surface without any oil or grease. So this is the best preparation before we weld the parts. So it's a good way to install this technology just before the welding process itself. But we also can use this short pulsed laser for changing or adapting the tribological things of materials. Here with this example you can see some oil dimples made with such a short pulsed laser. Typical diameter for such a little oil dimple is about 40 to 60 microns. The depth of it is about 5 to 8 microns, a very small one. And we need, of course, post-processing to remove the burr. But after this process, we have a lot of these little holes where we can have oil in it. This can be used, for example, in the motor, in the engine, in the area of the cylinders. The same technology, we also can increase the friction. Here's another example of a conrod, and before we bring in these bearing seats here, what you can see here, we like to use the laser here shown on this little picture to increase the friction, because with this technology we can be sure that the bearing seat is done in the right way. We can use our technology, the laser technology, here you can see the principle of it, to bring typical surface, what you can see here, to the inner side of this bore. Same way here, another example, even here we want to increase the friction. In this case it's a cam part. Before we bring it to the cam shaft, we can use the technology even here to increase on the inner side of the cam the surface friction, and then we can assemble it with the camshaft itself. So at the end of the presentation now, I just want to give you some ideas together with my colleague Hakan Kendici. These are, just want to tell you again, these are research topics. The first thing I want to show you an idea of TRUMPF. Here it's the online thermography. What does it mean? We can use our optical systems for our solid-state lasers. We can equip it with a special camera, which was used for the welding process, what we saw before for the Seamline Pro sensor system. And we can add, for example, such an in-gas camera. You can see this little picture here on the left side. Without any additional light, we are able to check the quality of the welding and to get a lot of information about the laser spot, the melt pool width, for example, the melt pool length, for example, of course, the thermal trace width, and so on. And with this technology, we are able to give a lot of information for the quality process for our customers to show them the quality of the welding was okay, or there was a little problem, or you have to check the welding or whatever. So with this technology, this could be a really interesting example here for a mass production. How does it work? Here again the picture. This is our welding head, what you can see, and here we add on such an in-gas camera, and we have a look, coaxial look with the hot beam. This is the way for the hot beam, so somewhere here's the welding process. So we can have a coaxial look with our camera systems directly to the process and can get a lot of different informations to check if the welding was good or not. Here are some examples what we can see with this technology. It's for example, a fusion fault, some partial or full penetration information here on the second slide, here, second picture. We can get information about the seam width, the holes, cuts, and so on, and of course spatters. This is just an example for you what is possible with this technology, and we will get more information in our labs worldwide to improve the welding results. So far, ladies and gentlemen, this was my part. I will hand over now the microphone to Mr. Hakan Kenderci. He will show you some details about the laser welding process below atmospheric condition. Thank you so far.
So hello also from my side. Now is Hakan Kenderci speaking. I want to tell you a little bit about laser welding below atmospheric conditions. If we are looking in the first picture to this welding on the atmospheric behavior, then we see that we have a very big vapor torch and a lot of spatters. In the next few pictures we see that we go step by step in deeper pressured area down to 500, down to 100, and also down to 10 millibar. Then we see that the vapor torch and also the behavior of the spatter is changing. On 10 millibar we see that we have nearly no vapor torch or a very small vapor torch and nearly no spatters. If we are looking now to a real part who's welded on the atmospheric behavior, then we see that it's already a good quality if we are looking on the surface of the welding, and but it's still improvable if we are going a little bit more down with the pressure. We will see in the next pictures. But at first, if we are looking on a movie who's made on a high-speed camera system in our laboratory, then we see that we have a very good surface of the welding. But we see that we have here a little turbulent melted area who bring us a little bit spatters here. You can see the spatters here on the welding zone. If we are going down to 10 millibar, then you can compare these two pictures and you can see that we have a very smooth welding surface, and also we have nearly no spatters here. And if we are looking now to the high-speed camera, then we can see that we have a very smooth and very clear and very lesser turbulent area on the welding zone, and we have nearly no spatters here. Sometimes you see some spatters here who's flying up, but not like the welding in atmospheric behavior. But it's not only the quality of the welding, we can also save energy. If we compare these two different pressure areas from the atmospheric to the 10 millibar, then we can weld with the same parameter deeper inside the material. Here we are welding 10 millimeter stainless steel, and you can also save energy up to 30–35%. It depends from the material and the speed of the welding. So now we can talk a little bit about the conclusions, and then we are finished. My colleague told you a lot of things about our machines. TRUMPF-Laser-based solutions for high volume automotive production. Laser technology is an enabler for lightweight design and helps to reduce CO2 emissions in production. TRUMPF, I hope you know it, is more than just a laser source supplier. We can automotive production. We have automotive production know-how, global coordination, sales and service support, systems, and turnkey solution with our integrators or partners. I thank you for your attention, and I hope that you have a lot of questions now. Thank you, Lord.
Well, thank you to Oliver and to Hakan there. A really interesting presentation, guys. We now have the polls that you mentioned earlier on, the online polls. So for all of our attendees, you can see on the screen, you can answer the question. Do you see potential for laser technology in your production? And you can now select your answer. And our second poll question is coming up. In which part of the process chain are you interested? And you can see a multiple choice question there, so if you'll make your answers. Thank you. And our final poll question, are you planning to invest in laser technology in the future? Very burning question, I'm sure. So if you can answer that, that would be very helpful. Thank you. Okay, now we move on to our Q&A session. So Oliver and Hakan, we have some questions for you. Bringing over. One of the questions that came in, guys, welding of differentials, is this done by radial welding or axial welding, and why? Which method?
Hello, this is Oliver Müller again. Nick, can you please repeat the question?
Oh, sorry, guys. The question is regarding welding of the differential, I think, which we showed earlier on in the presentation. And the question is the welding of the differential done by radial welding or axial welding? Okay,
I got it. Well, we have both in mass production. So this is just a matter of the design of the part, especially for front axle systems. And axial welding is used very often. In the rear axle, it's mainly used the radial version. The only problem here could be if you compare an axial with a radial welding. We have a shrinking process during the welding itself. That means there is no chance if you have an axial welding for a shrinking of the material. So there is a higher risk, I would say, for some cracks coming up if the design of the part is not done in the right way. If you have a radial one and we have a good design, there's sometimes the possibility for the ring gear to move a little bit during this welding process, and this is better against cracks. Yeah, so both is in production, but we have to think about the design itself. If the stiffness is too high, usually radial welding is much easier to control.
Thanks, guys. We have another question here again from our friends at Mahindra. The question is, what is the weld depth required for diff case welding?
This is also a question we should ask the car maker or the product. Yeah, in the production of these parts. Usually it's between, let's say, 4 and 5 millimeters. Some of them is maybe 3.5 to 4 millimeters. This depends on the motor, the engine of the part, on the, let's say, the torque of the engine. Yeah, So we have a lot of different differential gears in mass production. Some suppliers are producing for, I don't know, 20 car makers, different parts, and we have a lot of different penetration depths here. But I would say between 4 and 5, this is the common way, 4 and 5 millimeters.
Thanks, guys. Another question here. I'm going to try and be clear about it. So the question is, can we weld spur gears of the same diameter and modules together? The question follows on, can we blank smaller thickness gears and then weld those if possible? But if we want to answer the first question, can we weld spur gears of the same diameter and modules together?
This needs to be tested. I think it's always the same question if we get an inquiry to weld different materials, different parts. The best way is if the customers or the interest people will send some information, provide some information about the material itself. This is the first question, the penetration they like to reach, for example, and if it's a really stiff design of the part, even here we can improve it together with the customers in our labs. But it's very important, first of all, think about the material, the joining partners. If we have a carbon equivalent of 0.25 and higher, we have to think about maybe to weld it with a very slow speed, for example, to bring in a lot of energy that we have not a very quick cool down process, let's say. Then there is a risk for some martensite structure in the material, and then there's again a risk for cracks. So it's always the same questions. If the customers like to weld different parts, please get in contact with us, send us your inquiries. Sometimes just a principle or a sketch is okay for us. We don't need all the information if there's an NDA or whatever. Information about material and a little bit about the design. This will help to answer your questions.
Actually, guys, the question is just sent us a quick note to say that the material in question is C45. So,
yes.
But I mean, obviously, if you want him to, he can get in touch with you for further details, maybe on that.
Yeah. It's possible. This is also a question of the design partner. Very often we have the C35 on the left side, on the right side. This is the question if this is a conventional steel material. Together, the mixture itself, this is the question, what is the carbon equivalent? Is it weldable or not? What is the hardness after the welding process? So in our labs, we are able to weld it together with the customers, then we can make a cross-section, we can measure the hardness, and we can get out some information about the process. Is it a good one, or is there a risk, for example? Yeah? If the hardness goes higher than, I would say, 450 HVs, 500 HVs, there is still a risk if the stiffness is very high of the design of the part. So this needs to be discussed with the customers. But yes, we have application in mass production with C35 and another material in combination.
Thanks, guys. We've got all the questions for you here. Next one's more of a general question about laser welding, and the question is, what's the current trend for laser powertrain welding? Is it CO2 lasers or disc lasers?
I would say that there's a complete change. 4 years ago, we had maybe, I don't know, 90% CO2 solutions in the market. Nowadays, even the car makers, they like to have green production. You know, the energy consumption of a production line is a very important question nowadays. And with a solid-state laser, it's quite easy to reduce the electrical consumption, for example. If you compare CO2 laser, we have roughly 10% efficiency compared with a 25% or higher with a solid-state laser. This is a very good thing on the one hand side. And, of course, it's easy, really easy to integrate if we talk about a solid-state laser, because we have this flexible fiber cable in between the laser source and the welding optic. So it's quite easy to create a production machine or a welding machine which is equipped with a welding head, and we can use our lasers which are available up to 6 exits with one laser for these fiber cables. So these are some ideas why we have this big changing. I would say nowadays and in the near future, the solid-state laser is the solution for powertrain welding.
Thanks, guys. A question here, more of an application-based question. I think it's referring to the reduced noise in laser welding of the diff case. The question is, how is this achieved?
It's also a good question. If we have the laser welding in case of a differential gear, we always have a little distortion with all welding process. There's no welding process available without distortion. But the question is, which process is the best one with the lowest distortion? Bring we in a lot of energy or not? This is always the question. When we develop these weldings in case of the differential gears, we also develop the clamping device, how to clamp the parts, and with this combination of low heat input, low distortion from the welding process, and the same way with a special clamping device, it was possible to reduce, let's say, the distortion after the process to a very small amount. So this was the idea to use the laser technology. Yeah? In that case, with lower distortion, we have more accuracy between the bevel gear and the ring gear, and it's a very safe process so far compared with other processes. So this is the reason why I would say, if we talk about welding process in case of differential gears, I would say it's more than 95% is laser welding. There are some research done in labs to use other possibilities, but so far it's only laser welding.
Thanks, guys. You may have actually touched upon this in that previous answer, but the question is, what is the distortion in the ring gear, the differential gear, in the case of laser welding with the differential case? So what level of distortion in the ring gear?
We are talking about a few thousands of a millimeter. We can measure it. We need special machines for it. It's the question between the play between the bevel gear and the ring gear, and therefore are machines available to measure it. But it's really low, the distortion itself. So this is the reason why all of them are using this technology to weld it. If you compare it with a bolted version, we have some bolts around the diameter of the parts, and where we have the bolts, we will pull the parts together. In between the bolts, we will lose it again. So if you turn the parts, it's a kind of sinus if we measure the distortion. And if we compare it with the laser welding, we have a 360 degrees welding around the part, so it's more constant, much more, it's better than a bolted version, and well, it's really low, the distortion. So this is the reason for it. Yeah?
Thanks, guys. Again, a question I think regarding CO2 lasers or solid state. The question is, what is the sort of state-of-the-art laser application for double clutch laser welding? Is it CO2 or versus solid state? Which one?
Yeah, well, we started in 2004, 2005 with the first installations. There we had our machines equipped with a CO2 laser. They're still in mass production. A lot of double clutches are produced with the CO2 laser technology. But since, I would say, 4 years now, we have a complete change even in the double clutch area from coming from the CO2 laser to the solid state laser. Because if you see these production sites, for example, at Volkswagen, at Daimler, and so on, and we have a lot of different stations there, because the laser weldings, what I showed in the presentation, you saw a lot of different weldings per double clutch. So we can use one single source with more than 2 or 3 exits for the fiber cables. So we can use one laser for 3 or 4 or 5 welding cells. This is more a question of the production philosophy. But nowadays, I would say, if you see the latest developments all over the world for the double clutches, this is solid state laser, what is used for the mass production.
Thank you. Actually, this next question refers probably to you, Hakan, and the last portion of the presentation. Using low pressure welding, is there an influence on the maximum measured hardness in the heat affected zone near the weld?
Well, I try to answer this again, Miloshen, because otherwise we have to change the microphone again. Well, there is also an influence to the microstructure, of course, but if you compare the welding, if you have cross-section of the welding is very small, it's very narrow compared with a welding done under atmospheric condition. So that means the influence is smaller compared with welding under atmospheric conditions, but there is one, of course, with any welding process. But if you, and I think this was the idea from Hakan to show you in the audience, if you compare these two weldings, the one was made under atmospheric, the other one under 10 millibars, for example, we were able to weld the parts with the same parameters, that means laser power and welding speed and so on, and we reached, with the welding under 10 millibars, we reached really much more deeper welding, and it's much more narrow. There's not this, we call it nail head on the top of the welding, for example. It's more parallel compared with an electron beam welding, for example. And there are a lot of really good advantages using this technology. It's going to be really interesting. It's done in our R&D department, and we have some new ideas here, not only to improve the process from the side of the quality, let's say less spatters, less contamination of fumes of the surface of the parts, and then on the other hand we have the possibility to reach really deep weldings. We also made some weldings already with penetration depths up to 20-25 millimeters with this technology, and this opens maybe a complete new way for a welding process with the laser technology. Compared with the EP welding process, I would say the biggest advantage is we don't need this really deep pressure or vacuum, let's say vacuum in case of the EP welding. We just need a pressure between 10 or 20 millibars, something like this, and we can reach really a very, very good welding result. And we can use our network, laser network. That means we can have 1 or 2 or 3 exits per laser, and we can have 2 of these little chambers. While we are welding on the first one, we can evacuate the second one and the third one. So the evacuation time is nearly 0 in such a concept.
Thanks, guys. We've got a question here too. Could you explain again the effects on the welding process without filler wire? I mean, can you do that quickly, or is that something you'd like referred back to you at a later date, or you can quickly describe it?
I think I can give some ideas, but the best way would be if you're interested in to get more information about this, please send us an email. We'll get in contact with you. We can provide more detailed information about this. But just in a short way, if you like to weld in case of the differential gears without filler wire, we don't need any gap or preparation of the edges. We need one sharp edge on one side for the camera system, and the opposite side a little chamfer, which is, let's say, from tolerance side, we can give all this information to you. This is no problem. Even the parameters, let's say it's about 4 to 5 meters per minute welding speed, but this depends on, of course, on the application, and therefore I would suggest to get in contact with you directly and maybe to plan some welding trials within our labs of TRUMPF.
Thanks, guys. Another question we got. A lot of questions for you on this subject. How do you determine the laser weld diameter?
What do you think with the laser diameter?
Yeah, how do you determine the laser weld diameter is the question.
Cannot understand really this question, but this is always a question on the design of the part or the torque you have to transmit with this part. So to reduce the diameter of a welding diameter, whatever, this is more a question of the design and the engine and the torque of the engine, for example, which is allowable with the part. This is not a question for the welding process itself.
Okay, we have a question here. Apparently Daimler is using laser welding without filler wire. And the question is, are they using a radial or axial welding process?
So far it's a radial one. It's, as I already mentioned in the previous questions, radial one is a much safer process compared with the axial version. But I know there are some designs, of course, available in the market, and we already made some tests. But once again, the safer process can be reached with a radial welding, always.
Thanks, guys. We've got time for just one more question. The question is, regarding the investment in SF laser machine, how does it compare to other technologies, and has the cost for laser welding technology reduced in recent times?
Yeah, this is really a big question. It's not easy to answer. Well, TRUMPF can provide a lot of information about the welding process, the laser sources, the efficiency of the laser sources. We can provide an Excel file when we get this information of the customer, what he likes to weld, what is the cost for the electricity, for example, the gas cost, and so on. If you compare it with other applications, for example, I would say it's a very efficient welding process. And well, as I already mentioned, with the new or the latest technology of the solid-state laser, we are able to reduce the consumption costs. If we use a solid-state laser, for example, it is possible to weld without any welding gas. But sometimes we can use a welding gas to improve a little bit the surface quality of the welding, but we don't need helium, for example. If you have a CO2 laser installed in your production, you always need helium, for example, for a deep welding process, and I'm talking about laser classes higher than 3 kilowatt. And as you know, helium is a very expensive gas. I think all of you using when you're using the laser technology, you got some information of the gas suppliers that helium, there's a risk of supplying helium in the near future. And of course, this was another big advantage of the solid-state laser, to use other gases, for example, nitrogen or argon or whatever, much cheaper gases. So altogether, the efficiency of the laser, of course, welding without any gases, for example, and for me it's also a very important thing to integrate this laser. We can have very easy integration to production lines compared with CO2 laser. This is more complex because we need a mirror beam delivering system with a CO2 laser, and these mirrors and so on, they need to be adjusted in the right way and so on. I think the people using the CO2 technology, they know about this. This is not necessary anymore with this technology, with the solid-state laser. I think it's much easier to handle. But of course, even on this technology, you need some experience, but therefore you can ask, of course, us, TRUMPF. I think we can provide a lot of information for these special questions.
Thanks very much, guys. We're out of time for the Q&A. We've had a lot of questions, some quite in-depth technical questions, especially from the guys over at Mahindra, so I'm sure they'd be interested in hearing from you. You can perhaps clarify some of their questions a little more directly than over the webinar as it stands at the moment. Thanks again. Thank you very much to all our attendees for joining us today, and thanks very much for Oliver and Hakan. It was a great presentation, very interesting, really good, some excellent videos. Very well done, guys. Very informative seminar. The webinar will be uploaded into our archive and it is available in the future. So any of your colleagues who were unable to attend or listen today can reach it. You can access this by any previous webinar under the webinar tab on the Automotive Manufacturing Solutions magazine homepage. Thanks again for joining us today, and we'll hope you'll join us again for our next webinar. Thank you.